Okay, so let's look at one like this. So we have a more complicated rate function here. It's not a straightforward antiderivative, so we know we're going to have to chisel at this with some kind of technique. And so we ask, what's the first question we always ask? Is it undoing the chain rule? So what do we think? Is it undoing the chain rule? No, we can think about that denominator as to the -1, and maybe it's natural log, but then what? That numerator would have to be the derivative of that denominator, and that doesn't work. Okay? So this particular one, we have a technique, but it's kind of in disguise here. Do you see what technique is going to work, but it's kind of in disguise? Do you see? So do you see that this is kind of like squared, and this is like squared, and then to the first plus 2. Yeah, okay, so someone mentioned, if you notice, this is kind of like a quadratic polynomial, right? But with these e's, it's kind of in disguise because these e's are kind of diverting our attention to see that this is really something squared plus a linear term plus a constant. So that's kind of like a quadratic polynomial. And what kind of technique do we have for a polynomial over a polynomial? That was our partial fractions, right? For rational functions. So here's what we can do. We can kind of get rid of that distraction of the e's by saying, let's let u equal e to the x. So what we're doing is we're going to actually change the variable. We're going to do this substitution. Everywhere there's an e to the x, we're going to put u, and that's going to change the variable of the integral into u, but kind of maintain the accumulation function, right? Maintain what that whole accumulation function is, but just in a different variable, u, where u is e to the x. Okay? So then what is, e, so then e to the x squared is the same as e to the 2x. What's that in terms of u? It's u squared, right? So that's e to the 2x. Now there's only one more thing we're going to need is dx. Okay, so how can we find dx? Well, we can do a mini derivative on u equals e to the x. So if we kind of do the derivative here, but let's do the differential version. Du equals e to the x dx. So that's the differential version of taking the derivative, right? Du equals e to the x dx, the whole chain rule there. Okay, and so then what does dx equal? So we're thinking about changing this whole thing into u, so we got to know what dx equals. Dx then equals du what divided by e to the x. But what's e to the x? That was just what we said was u, right? So e to the x is just u. So dx turns out to be, if we do the algebra, du over u. Do you see it? Okay, so by saying that u is e to the x, that leads us to the fact that dx is du over u. Just by doing the little derivative and then doing the algebra. So now we're ready to rewrite this as e to the 2x equals u squared. E to the 2x again, u squared plus 3u plus 2. And then dx was? Okay, so now we just do the algebra correctly. All right, so just do the algebra. because I have u squared up here and u down here, I can simplify that, right? How does that simplify? See that? So then it's just, I have a single u in the numerator. Now, if I didn't have a power of u in the numerator, what would happen to this u? It would just get multiplied by this denominator, see that? And we can handle that with partial fractions. But in this case, since I have a power of u in the numerator, it can go away. But if I had something else, like maybe u squared plus a number or u minus 1 or something, and I can't do that simplification, well, then u guys has to latch on with that denominator, okay? So once you substitute in, you just have to follow arithmetic and algebra correctly. You can only do that cancellation because you've got also a u in the numerator. Okay, so now what do we have? We have integral of u over, now what about this? What was our requirements for doing partial fractions? 2 requirements. First requirement is degree comparison, right? Numerator has to be less than the denominator, right? Got that, because now we have u to the first and u squared in the denominator. And then, other thing, got to be able to factor that. If you can't factor that, can't do partial fractions. This one factors easily. And then, so we have the kind of the easiest partial fractions problem that there could be. It's just basically going to be a over u plus 1 plus b over u plus 2. So I'm gonna streamline this, assuming that you can check this later, but a plus b is going to equal 1, and 2a plus b is going to equal 0. So then a is negative 1 and b is 1. Nope. A is negative 1 and b is 2. There we go. Okay, so I don't expect you to be able to do that fast, but you should know how to do this problem, and you can just check it later. But I think this is right. Is this right? A plus b equals 1. B plus 2a equals 0. That's right. Subtract. Negative a is 1. Is negative 1. These 2. Okay. So then we got, so this a then equals to negative 1. B is equal to 2. And so the point is that once we get this thing into this new variable u, that we can use a technique, and then we're going to take it all the way to the antiderivative step, and we're going to do the antiderivative in terms of this new variable. That's the whole point. That now in this new variable we can do the antiderivative, which will be negative natural log of absolute u plus 1 plus 2 natural log of u plus 2 plus c. And then after you take the antiderivative, we want, the problem's in x, so we want it back in x. So it's going to be natural log of what? What's u plus 1? E to the x plus 1, because u is just e to the x, right? So now after you take the antiderivative, you switch back. You switch back to your original variable. We got it. Okay, any questions on that? Do you follow? Okay, so now what if we had a definite integral? So a definite integral. So suppose, I'll just do it in red here. Suppose we want to take this from like 2 to 9. So there's 2 different ways we can approach this now. We could just, when we change it to u, the limits aren't going to be, we don't have x anymore, so we're going to just take the limits off. And then once we get to this last step, then we're going to go back to evaluating from 2 to 9. Make sense? So once we get that antiderivative in terms of x, then we're going to evaluate that whole expression. The net change from 2 to 9, right? The net change of that expression from 2 to 9. Or, what's an alternate way? If we have a definite integral, then if x is 2, what is u? X equals 2 means u is what? E squared, right? According to the way we defined u. And then x equals 9 equals? Means u equals e to the 9th. So what could we do instead? We could just, if we have this definite integral, then instead we could come here and we could just evaluate this expression using the corresponding values of u, right? So we could evaluate this expression from what to what? From e squared to e to the 9th. And that would work as well. So if you have a definite integral, then you're actually getting an amount of net change, a value of net change. You can do it 2 ways. You can switch back to the old variable and use the original limits, or you can just use your antiderivative in the new variable with the corresponding limits of the new variable. Your choice. But if you're doing an indefinite integral, you need to switch back, because if you're asked to do that antiderivative, your answer is going to have to be in terms of x. Okay, questions on that one? Doesn't make sense. So this is called a change of variables technique, or u substitution. Okay, u substitution. Can I erase this one? All right, so how about this? First question that we ask. It's the first question we ask. Is it undoing the chain rule? Is it undoing the chain rule? Yeah, so no way, right? So this does not fit that pattern. That won't work. So think of our other techniques, right? So is it undoing the product rule? Probably not. Maybe you could make it work, but it wouldn't be fun, right? So that would be ugly, and it probably wouldn't work. So normally we've got the common forms for undoing the product rule, like x times sine x, or x times e to the x, or forms lots of forms involving natural log, or the inverse trig, some inverse trig functions. So this doesn't really fit the bill for undoing the product rule. So can we apply this new technique to get something that we can do? So the question is, what do we set u equal to? So where's the problem with this one? Where's the log jam in this that we want to set free here? Yeah, this denominator, right? Especially the square root of what? Of a sum. Square root of a sum. That's really, that locks things up for us. We can't really do much with that. So we can let u be what? Yeah, so if we let u be just what's under the square root there, then this the square root of u, that's just like u to a power, right? That's just like u to the 1/2, and that is a lot, could give us a lot more freedom in the whole expression, okay? So let's do that. U is 1/2 x plus 1. Okay, so what are we going to need? We're going to need to find x. So to make this whole substitution now, we're going to need to find x, or we're going to need to find dx. So how can I find x? If u is 1/2 x plus 1, then what does x equal? u minus, we would subtract 1. We just solve for x, right? Just solve for x. It'd be u minus 1. And then last step, times 2, right? So I just solved for x all in one step there. Imagine subtract 1, then I need to get rid of the half, so I multiply by 2. Okay, and so I got my x, and I could, if I want to change that, I could just go 2u minus 2. And then what about dx then? Dx is simply 2 du. Okay, now we got everything we need to change this into variable u. So x is 2u minus 2, and then having the minus 1 squared over square root of u times 2 du. Stop me if I lost you. Okay, so then this is really 2u minus 3, right? 2u minus 3. So the question is 2u minus 3. And then I'll write this as u to the 1/2. And then I have a 2 du. Okay, so did it help? Oh, sorry, squared. Did it help? So here you just have to see what you can do to get this into a form that we can actually make progress in terms of antiderivative on. What can we do? Yeah.
You could multiply the top out, so you have a sum. You can split it up.
Yeah, right. So if I just multiply this binomial, I'm just going to have 3 terms, all powers of u. And then I could just divide each one by u to the 1/2, and then I just have a polynomial. That's the kind of thing that, things like that will show up in these, and you have to be able to see it. Like, if I distribute, can I get something I can do? If I multiply out and break up the fraction into separate terms, will that help? So you always be on the lookout for just rearranging with algebra that's going to help. You just have to be on the lookout, because there's no way to do every example of that. So you have to be on the lookout for that. So what do we have? So we're going to have, I'll just pull the 2 out in front, and we'll have 4u squared minus 12u plus 9 all over u to the 1/2. And do you see how we can see the light at the end of the tunnel here? What are we going to do? Break it up, right? So break it up. When you have one denominator and terms in the numerator, sometimes what's the thing to do is break it up into separate pieces. We've seen that before. So we had 4u squared over u to the 1/2, which would be 4u to the 3/2 minus 12u to the, anybody? You're all thinking it, right? 1/2 plus 9 u to the, and now it's just power rule. 3 power rule problems, right? So I'm not going to finish it. We'll just say, so 1 power rule, antiderivative. And then what's our last step then? Replace u's with 1/2 x plus 1. So we back substitute. One half x plus 1 for every u. Okay, any questions on that? So just another, we won't finish it. I'll just see how you would start. So x times, here's another one. So that's the cube root. X times the cube root of x minus 2. Is it undoing the chain rule? What small change to that would mean that it's undoing the chain rule? This is cube roots. That's what I'm trying to show here. Cube root. So do you want to change this to x squared or this to x squared? If we change that to x squared, do you see that we would be undoing the chain rule, right? But it's x to the first. Undoing the chain rule won't work. So here's a chance to do the U substitution technique. What would we say? U equals x minus 2. Again, getting a sum or difference out from underneath a radical allows us then to have u to the 1/3, which we can work with, right? We can work with that. Okay, so you finish. This one's a lot easier than the one we just did here. That's much easier. So you got to get your x. That's easy. Get dx. That's easy. Substitute, and then figure out how you're going to use algebra to get something that you can do the antiderivative of. Do it. Substitute back in x minus 2 for every u. Okay, questions on that technique? You'll have some web work for Wednesday on that. All right, so let's talk about what's called improper integrals. Can I erase the screen? So improper integrals. So here's a kind of a scenario here. So consider a rate of change function that is always positive. So for example, a population grows by 2,000 people per year. So there's some population growing by 2,000 people per year. And so an improper integral, an application of that, the idea is kind of the long-term result. So what will happen to the accumulation of the population if this rate just continues on indefinitely? So if x is just allowed to, if the number of years is just allowed to increase indefinitely, so in the long run, in the long term, what will happen to this population?
Do the same thing, just 2,000 times faster.
So in the long term, what's that? Someone said something. He said it approaches infinity. Agree with that? Yeah, it's just going to get really big. The population's just going to keep getting bigger and bigger and bigger and bigger. Okay? So the population will grow infinitely large because 2,000 people is added every year for an ongoing number of years. So what am I, relative to this problem, what am I showing here? What's that? That's the rate of change. 2,000 per year, right? Constant rate of change, 2,000 per year. So the accumulation will look like what? Up and up and up, right? Up and up and up. So the idea of an improper integral is what happens in the long term? What happens in the long term? So here, with this constant rate like this, a positive constant rate, it's just the population just will explode. It will get as big as you want it as long as enough time goes by. Okay, so here's a rate of change function. It's positive for all x, 1 over x cubed. So the rate of change, this is also a positive rate of change function. So then what can be said about this net accumulation function? Okay, the net accumulation from 1 to x of that rate dt. So if that rate is always positive, what can you say about that net accumulation function?
Will also approach infinity in time.
Yeah. The accumulation will approach 0. So the rate of change is always positive, so the accumulation approach 0. So the rate will approach 0. You think about the rate? But this is a positive rate of change, right? It's positive. What happened in the previous example if the rate was positive? You keep growing, right? So your accumulation just keeps growing and growing and growing. So is that true here as well? Okay, well certainly it's going to grow, right? So certainly if you have positive rate of change indefinitely, your accumulation will always increase. That was kind of the answer I was looking for to this. Accumulation will always increase. Okay, so then how much will it increase? So what about the limit as x approaches infinity, meaning let x get really big? And what about the value of this function? In other words, the integral from 1 to infinity.
It'll also be infinity.
The integral from 1 to infinity r sub ft dt. What do you think, Scott?
It will also approach infinity.
Because?
Because the rate stays positive. It doesn't matter how small it is. It's still positive.
Okay, if the rate is positive, doesn't matter how small it is, it means the accumulation is going to keep growing. So then this limit will just get really, really big. Agree? Okay, let's do the math. Let's do the math and show it. So so what does doing the math mean? It means kind of evaluating this definite integral, right? So for this rate of change function, how do we evaluate? So it's not a of infinity. You don't plug infinity in, but you look at the limit as x approaches infinity. Okay, so the way that we do that is we say that this equals to the limit as, say, a approaches infinity of 1 to a, and then we have the rate function, so 1 over x cubed dx. So we can't plug infinity in, but we can look at a limit. We can look at what happens as numbers get really, really large. Where is it heading? Where is our accumulation function heading as that upper bound of integration gets very large? So I always want to start by rewriting an improper integral this way. And now we can evaluate the limit when all's said and done, and we can work on this integral. Now there's going to be a fact that we need, and that fact is, let's just get that out of the way first, that the limit as x goes to infinity of 1 over x to the r equals 0 if, what has to be true about r for that limit? Julia got it. So all r has to be is positive. As long as r is greater than 0. Because if r was, say, 1/2, you'd be 1 over the square root of x. 1 over the square root of x, as x gets really, really large, that still goes to 0. So all you have to do is have a positive exponent in your denominator, any positive exponent, and that expression 1 over x to any positive exponent will equal 0 as x gets large. Okay, so we're going to need that fact, so let's just get that out of the way. Okay, so now we're ready to work on this. So we're going to hold on, do the limit at the end. And we're going to do the limit at the end, so now we can work on this. So antiderivative, 1 over x cubed. We die for ones like this now, right? 1 over x cubed is? X to the negative, first of all. Negative 2, right? This is x to the negative 3. We're going to raise power, and so then we'll need negative half. And then we're going to evaluate that from 1 to a. So we got the limit as x approaches infinity of, okay, what do we do? Plug a in. So it's net change, right? Net change from 1 to a. So plug a in. I'm going to go ahead and put that in the denominator. Negative 1 over 2a squared plus 1 over x to the minus 2, 1 to the minus 2 is just 1, so plus half like this. So I plugged a in, I plugged 1 in, and I subtracted, but it's minus, it could be minus and plus. This should have been a here. So then what's the limit of that expression as a gets very large? Yeah, so we're going to use our fact now, right? Because 2 is greater than 0, as a gets very large, this thing will go to 0. And that integral from 1 to infinity is 1/2. What about our conjecture here? What happened? Is that what we thought? No. We had this positive rate function. We said the accumulation is always increasing. And so then we thought, well, then the total accumulation, if we just let it go indefinitely, should be infinite. But not only is it not infinite, but it's pretty dang small. It's 1/2, right? Didn't even make it to 1. Okay? What's going on here? So what is it that's different about this rate function than my population example? Something's different here. What's that? Yeah, so the rate is getting smaller, right? So the rate is approaching 0. So it is always positive. So the accumulation is always increasing, but that rate is getting very small, right? Essentially 0 for large x. So then what happens to our accumulation? Kind of. Right, so what would that accumulation function look like? You draw it with your finger, what would that accumulation function look like? So it doesn't go up indefinitely, but it levels off, right? So here's our rate function. There's 1 over x cubed. Okay, and so what happens then for the accumulation starting at 1? So what happens is, yes, it's always increasing, but then after a while, it's increasing. That rate is so close to 0 that the amount of increase is virtually nothing, right? So even by the time we get to x equals 50, it looks like it's just leveled off, right? The bits of accumulation past a certain point are so small that this thing just virtually is just 1/2. And if I zoom out on that, zoom out on the x-axis. Okay, does that make sense? So these improper integrals, they're actually interesting because they don't just all go to infinity, right? You've got a situation where, yeah, your rate is always positive, and so yes, the accumulation is always increasing, but then by such small amounts that it never can get above a certain level. It just, all it would do is approach 1/2 and never get, the total accumulation over infinite x is essentially 1/2 and never will eclipse that because that rate gets so small so fast. Okay, so then what about this one? So what about 1 over x? This net accumulation function. if 1 over x is also always positive, so that net accumulation function is always increasing as well. So what do you think? So 1 of x, does that get really small for large x? Does that go to 0? Yep. It's really small. And so then what about this net accumulation function? Because the rate is virtually 0 after a while, level off? Let's do the math. Here we go. Let's just do the math to show that and see what it accumulates to. So we're going to take the limit as a goes to infinity of the integral from 1 to a, 1 over x dx, which is the limit as x goes to a. Antiderivative, natural log. We're only dealing with positive x, so we don't have to worry about the absolute value. X is always positive in our integral here. We're going to go from 1 to a. And so then we get natural log of a minus natural log of 1. Natural log of 1 is 0. So we're left with the limit as x goes to infinity of the natural log. What does natural log do as your argument gets large? It keeps increasing and increasing and increasing. Oh, brother, nothing we're predicting is correct here. So what's happening here? So now we thought since the rate was going to go to zero, the rate's going to 0, the rate's going to get super, super small, that accumulation would level off. But what's happening to the accumulation? It's going to go to infinity, like natural log goes to infinity. So what happened? Why? I thought this is kind of the same situation as 1 over x cubed. So what's going on? Anybody? This is a really important concept here that we're talking about. Anybody venture a guess? Yeah? Is that hand kind of?
I don't know. It's kind of stupid, but if your rate of change keeps increasing, then it'll end up leveling off. If it reaches to 0, then it'll just the accumulation.
Okay. Yeah, Alec.
Be based on the accumulation function, like what the rule is for it. So like it determines where it levels off.
But why? So the question is, why did 1 over x cubed, why did that have an accumulation function that ended up flattening out and leveling off? When this rate function, it also goes to 0, but its accumulation function does what? Goes to infinity. Doesn't level off, right? So the black one is 1 over x over there, the rate function. So it's getting small. Okay, it's gonna approach and get very close to 0. But its accumulation function just keeps getting bigger and bigger and bigger. So why? Why did 1 over x cubed give us a finite amount of accumulation over the long run, whereas 1 over x did not? Alec.
Would it be because of like the power associated with
Okay.
x cubed would increase a lot quicker?
Right. Okay, so 1 over x cubed, how do you see? What happens to that rate function in 1 over x cubed compared to 1 over x? 1 over x cubed
Heads towards 0.
gets smaller a lot quicker, right? That rate gets smaller a lot quicker. This rate of change, 1 over x, it's approaching 0, but it's getting there. The rate at which the rate gets to 0 is much slower. And because of that, we're going to get more accumulation. In fact, we're going to get enough accumulation for this thing to not ever level off. It's just going to keep increasing and increasing. So the question is, what's the breaking point, right? So if we have that rate function, 1 over x to the p, for what values of p are we going to get a finite accumulation over the long run versus just it blows up? So where's the breaking point? Somewhere in here, there's the breaking point. Okay, so without proving it, and the proof isn't hard. You just do the integral again for 1 over x to the p, and just leave that generically open. But what it turns out to be is, as long as p is anything greater than 1,
P is negative. Is that just that
well then
you could just rewrite that as x.
then you have x. Then it just there's no question
Y
because
is just
your rate is increasing. If your rate is increasing, you don't even need to talk about the accumulation, right? So the only time when it makes sense to talk about do you have a finite amount of accumulation is if your rate approaches 0, right? If your rate doesn't approach 0, we got like the population example, and it's just going to blow up, right? So the only time that the interesting cases are when your rate heads to 0. If your rate heads to 0, then we're saying which of these in the long run gives us a finite amount of accumulation and which don't. So for this particular form of a rate function, if p is greater than 1, then this accumulation function, and this can be any value, say b, what we say is convergent or converges. Converges on a value, right? What do we see? When we had from 1 to infinity of 1 over x cubed, that thing converged to 1/2, right? And that was this value right here, 1/2. If p is not greater than 1, so if p is less than or equal to 1, then this integral is or diverges or is divergent. So that could, there's a couple different cases for that. That could mean that the amount of accumulation gets infinitely large or infinitely large negative. Or it could mean that the accumulation just keeps fluctuating, but it just never hones in on a particular value, right? So this could mean really big or oscillates indefinitely. Never hones in on a particular value. So for an improper integral to be convergent, it has to actually hone in on a particular value, like this one did for 1/2. Now, that's a very narrow class of rate functions. 1 over x to the p. That's very, very specific. How do you know about other ones? So then the next example I was going to do is this one. All right, so can I erase what I've got up there?
What would be an example of oscillating?
Yeah, so if the accumulation function ends up being like sine or cosine or something like that. Okay, so what about this? So here's this rate function in red here, 3x e to the 1/2 x. And I want to know about the total accumulation from negative infinity. So now I'm going to start at negative infinity and accumulate up to -2. So the question is, we're looking at this improper integral. So, convergent or divergent? And if convergent, what does it converge to? Meaning, what is the total accumulation from negative infinity to negative 2 if this thing converges? So this rate function doesn't fit that form 1 over x to the p. So we can't just look at the p and say, oh, p is greater than 1, therefore convergent, because we don't have that form. So in any other case, what do we have to do? We do the math, right? So we evaluate, do the math. And if we do the math correctly and we get a finite value and we take the limit at the end, right, we're going to start by changing this into a limit. And when we get to the end and we take the limit and we get a finite value, then we can conclude this is a convergent improper integral. If we work it through and we take the limit and the limit is like negative infinity or infinity, then that's a divergent integral. So any other case besides 1 over x to the p, we're actually gonna do the math. You're gonna set up the limit as a goes to negative infinity or you could do a to positive infinity of negative a to negative 2. And then the question is, how do we do that antiderivative? So we're going to have to do that antiderivative and evaluate it at the limits and then take the limit. 3x e to the 1/2 x. What technique is that? Undoing product rule, right? This is x e to the x. Don't have time. All right, so